Good morning. In the previous lecture, we started talking about particle shape analysis as a key ingredient of optimizing mechanical operations. As we discussed, virtually every mechanical operation involves processing of particles, and the two morphological characteristics of particles that play a key role in determining the efficiency and effectiveness of such processes are shape and size. And of the two, we started discussing shape analysis methods last time. Talked a little bit about how shape differs from size, the fact that it's a qualitative characteristic, but in order to represent it quantitatively, you have to assign certain sizes to it. So shape and size are very interrelated. And then we talked about various classes of shape determination methods, and in particular we listed 4 classifications: single particle analysis, bulk powder analysis, mathematical techniques, and verbal descriptors, and we discussed the first 2 in some detail. So, we will talk about the third one quickly. Mathematical techniques are emerging as the dominant method for shape characterization, primarily because of the emergence of high power, high speed supercomputers at extremely low cost, which enables us to take any particle and discretize it. You can actually take the profile of the particle and digitize it so that you represent it as points in a 3-dimensional space, and if you choose, you can just keep it as a digital profile. You do not even have to join the dots, so to speak, to recreate a contiguous shape. Or what you can do is do curve fitting. So, if you have a set of particle or dots or points in 3D space, you can curve fit these points to get a continuous profile or shape. Now, it is an interesting artifact that if you try to improve the accuracy of your curve fitting and minimize the error due to deviation of your continuous curve from the discrete data points, sometimes the resulting shape can actually be farther away from the real shape. In other words, mathematical curve fitting of discrete data, and it is not just for shape analysis, it is in general, you have to, the error involved can sometimes be reduced by going farther away from reality in a sense. So, the advice is that as far as possible, don't try to use curve fitting algorithms that try to minimize the error. If you are going to do curve fitting, then use an iterative process where periodically you go back and compare the curve fit profile versus the actual profile, and then see if you are converging or diverging. Do not just rely on the mathematical error formulation. The third method that can be used in mathematical analysis is the Fourier Transform type of analysis, where you try to capture the key or dominant characteristics of the profile, have a library of similar Fourier Transform profiles, and compare the Fourier Transform signal of your test particle to those in the reference library and try to find the best match. So, these are the 3 techniques that are based on essentially doing an imaging of the particle, discretization of the profile of the particle, and then either doing digital analysis or doing an analog characterization of the particle shape. The fourth method, verbal descriptors, is almost the exact opposite, which basically says you can do all this and you can get a very, very precise fit or digitized map or any of those other methods based on tangents and intercepts and so on, but ultimately what you need to do is communicate your findings to somebody else. Now, if you are in industry, you may have to communicate to another factory. If you are in academia, you may need to convey your results to another research lab that is working in a similar problem elsewhere. For example, again talking about space samples, the same samples may have been distributed to 10 different labs and all may have been asked to analyze. Somehow you need a way of translating your findings into a form which is understandable for all these labs. Then what we have done is develop certain standard terminology for describing the particle. These are called verbal descriptors. For example, spherical is a verbal description of a particle which quickly conveys that it is a sphere, right, but that is an easy one. But there are also terms such as a fibrous particle, right. When you say fibrous, labs across universities, countries will realize what you are talking about, it is shaped like a fiber, or it could be rod like. A rod is typically a cylindrical kind of a shape which has a much longer length dimension compared to the diameter, or it could be needle like. So, there are certain standard terminologies that have been developed which provide verbal descriptions that are quick, that can be quickly communicated to various labs around the world, and people can understand what you are talking about without necessarily having all the data transferred to them. One of the problems is, as data gathering becomes easier and easier, the amount of data that we are generating is also becoming larger and larger, and it is becoming increasingly difficult to actually transfer data from one laboratory to another. And so, it is kind of ironical that as our ability to collect data increases, our reliance on the more qualitative verbal descriptors is also increasing, because we just cannot take all this data and move it over. So, we typically store these data in some place, maybe in the cloud, and people access it on a as and when needed basis. Okay. So, these are the 4 very basic methods of shape analysis, but you have to somehow establish a systematic way of doing this. As I mentioned in the last class, shape analysis is essentially a pattern recognition exercise, and pattern recognition is a science that is not restricted to shape analysis alone. It is used in many different fields, right. So, there have been a set of guidelines and rules established for pattern recognition in general, which can very easily be applied to shape analysis. So, when you do pattern recognition, there are actually 3 steps in that. The first is you have to have a selection of candidate patterns. In other words, you need a library of some kind, all the patterns that have been analyzed by various people and classified in a certain way, right. So, the first thing is to have these selection or candidates from which you select a pattern. The second is, and this is the most important one, is decision rules. You have to formulate certain rules that you are going to apply in order to decide whether a pattern that you are examining matches one of the patterns in the library. Okay. And the third part is simply the decision process. So, the second part is certainly the most crucial one in terms of applying some of these decision rules to decide which is the best matching shape. Now, part of this exercise is also to screen all the data that you have and decide which are the relevant data and which are the irrelevant data, because once again we are now in a generation or age where there is a surplus of data on everything. So, when you are looking for shape analysis, you have to be very clear what is data that is relevant for your analysis and what are the data that are not, and you should be able to immediately dump all the irrelevant data and focus only on the relevant data in order to do your pattern matching. So, that is another important step in your decision making process. The other decision you have to make is what level of detail or sophistication do you need in your analysis. The simplest way to analyze any shape is to start with a simple visual inspection, a gross inspection, typically not using any magnification or lighting. You have a human observer that examines a particle and ascribes a shape to it. Most of the time that is enough. If it is, you stop right there, but in certain cases it may not be enough. So, you have to make a conscious decision that you will progress beyond the simple gross visual inspection and start using more precise techniques for shape mapping. So, that is the third step, the decision process of how far do you go. As we talked about in the last class, there is this law of diminishing returns that says the less data you gather, the better off you are, provided you satisfy your functional requirements. So, you have to have a clear and crisp way of deciding where you stop your shape analysis. But let us say that you have decided to go ahead and do a fairly rigorous shape characterization, then what are the steps you take? and here you go back to decision rules that apply in pattern matching. There are actually some 8 major decision rules in pattern matching. I'll just write them down here and then we'll discuss them. The first is called the distance function approach. The second is likelihood function approach. The third is trainable classifier. Deterministic. The fourth is a trainable classifier statistical. The fifth is syntactic methods. The sixth is member roster concept. The seventh is a common property approach. The eighth is a clustering property approach. Okay. So, like I said, these are techniques that are not necessarily restricted to shape analysis alone, but anytime you are trying to take a pattern and try to decide what it represents. Okay, so the first one, distance function approach, what do we mean? You know, just like you have the physical space in 3 dimensions, you can also define what is called a shape space. You can take certain descriptors that represent shape and draw a 3D graph from that. For example, you may decide that for a particular particle that you are trying to analyze, let us say that elongation ratio is an important parameter for you. You may decide that roughness is another important parameter in your application, and let us say as a 3-dimensional object, bulkiness is an important shape parameter for you. Okay. So, these based on your functionality, you know, where you want to use that particular particle, you have decided that these are the 3 important parameters. So, what you do is you take a particle that you are trying to analyze and locate it in this 3D space. Okay. Then what do? You take 2 reference particles from your library and see where they fit into this particle space, and let us say that they are here and here. Okay. So, based on this, what do you decide? You decide that this shape is more likely to be this shape than this shape, right. So, you discard this shape and keep this one and then select another shape that is much closer to where this is. So, let us say that this is a reference shape that you have in your library. Now, again you look at the distance in this 3D space, not physical space, we are talking about shape space, and see which of these is closer to your test object, right. So, you can imagine doing this iteratively until you find a particular shape in your reference library that most closely mimics or resembles the shape that you are analyzing. So, that is called the distance function approach. You estimate the distance between your object and various reference patterns in your library, estimate the distance in each case and try to minimize the distance. Right. There are many algorithms by which you can do this. The second approach, the likelihood function approach, is very similar, except that it deals more in the statistical aspects. In other words, what it really measures is the probability. It may, if given a shape that you are trying to assess and given two reference shapes, it tries to estimate the probability that this shape is close to the or resembles this shape versus the probability that it resembles the other shape, and what it tries to do is maximize the probability of one reference shape being exactly the same as the test particle that you are looking at. So, it is very similar to the distance function approach, except that it deals in probabilities, and part of the assumption here is that you do not have full confidence in your data, especially as particles become finer and finer. You really cannot exactly and precisely nail down what some of these parameters are, and so what you are really trying to do, and similarly the spectra in your reference library may also have uncertainties associated with them. So, the differentiator here, I mean this approach is for finer particles typically in the nano dimensional range, and it tries to account for the fact that there is uncertainty in the data, and therefore it kind of reframes the whole approach in terms of statistical probability, but otherwise uses pretty much the same algorithms as the first method. The third method, a trainable classifier, deterministic, again uses a process that is very similar to the first two, except that it kind of uses a neural network type of a concept. It is a learning algorithm. So, instead of the inspector randomly choosing shapes to assign for each comparison, the program or the algorithm itself kind of learns. The first time it tries to map a particle shape to something in the library, it draws certain inferences, and it actually can dump both the reference shapes, select a new set of reference shapes for the next comparison based on what it learned from the first classification, and so it is just like any neural network. The advantage is it is much faster. You are not randomly and empirically picking shapes for comparison. Your comparison software or program itself is applying its learning at each step of iteration, so the convergence to the actual shape is much faster. So, a good neural technique or neural network or trainable classifier can do this an order of magnitude faster than a simple distance function based approach. And similarly, the fourth method is the counterpart to the likelihood function approach, in the sense that it also uses a learning algorithm, but it works with statistical probabilities, right, and uses the knowledge that it gains in each iteration as a way to speed up the convergence to the actual shape of the particle. The fifth one, syntactic, is kind of similar to what we talked about earlier in terms of verbal descriptors. Syntax is basically the grammar, right. For a language it is a grammar. So, similarly for particles, syntactic techniques establish their own grammar, which is essentially the verbal descriptors that we were talking about. So, what that technique is saying is, if you are trying to compare a particle to something in your reference spectrum, if the particle is rod like and you have something in your reference library that is also rod like, you can ascribe that as the shape. So, It is a technique that is used more for the gross inspection that I was mentioning earlier, where you do not particularly care to pin down the exact shape precisely, but you just want an fairly high level understanding of what the shape is. This technique is particularly useful when you are looking for shape distribution among a set of particles, because in that case you are not going to waste your time trying to understand the shape of each particle. You just want a sense of the entire particle population and what is the mean shape that you can ascribe to the particles. The last three are kind of based on, I would say, set theory approaches. Member roster approach. So what this technique does is that it looks at clubs basically. It's a membership in a club type of an approach. Suppose you are examining a random particle with an unknown shape. You take one space in your shape space. Let's say it's here. So let's say that this is, okay, let me redraw this. So let's say that this is your actual particle. You take a set of shapes and see how it intercepts with this particle. And similarly, you take a second set of shapes and see how that intersects with this particle. Now clearly in these two cases, if you are calling this 1 and this 2, the membership category is different in the two cases. In the case of candidate shape 2, the particle you are looking at is entirely contained within that set, right. So the membership index is 1, so to speak, whereas with the other particle it is not clear that it is contained within that shape. So you can actually define the membership in this case. If it is completely outside, then its membership index will be 0. So in this case it is 1, in this case it is 0. So clearly you would say that this particle belongs in that set of shapes. And again you do this iteratively, you keep kind of narrowing down this set until suddenly the membership index goes from 1 to 0. Okay, so that is one approach, which basically says the membership can only be 0 or 1. If it is within the set it is 0, if it is outside the set it is 1. It is like a club membership kind of thing, right, either a member or not a member, that kind of an approach. But then you can also talk about graded memberships. For example, in a club, one person may be a life member, one person may be a visiting member, a guest member, one person may be a student member who has restricted rights, for example. So instead of the membership index being just 0 or 1, you can actually have a whole continuum of membership indices that range from 0 to 1 depending on how strong the membership is, in a sense. So similarly in shape analysis you can also consider a scheme by which this membership index varies from 0 to 1. So what you do, again, it's an iterative process. You take the particle whose shape you are trying to analyze, take two sets of shapes, see and then look at the membership index of your test particle in these two sets. Whichever set has a higher membership index, keep that one, discard the other one, and keep doing this iteratively until you find a set of candidate shapes that give you the highest membership index, close to 1 but not necessarily. Okay. So that is another approach that is used. Some of these may sound complicated when talking about it, but when you do it algorithmically it is fairly simple and straightforward. And as I said, these techniques have been well developed now and they are applied in a very wide range of fields, so it is not a big deal. The common property approach says that it's again somewhat related to the distance function approach, except that it says there must be at least one property of the candidate or the test specimen that agrees exactly with at least one property of the candidate shape. So you look for commonality, right. So instead of the first approaches that we have said, The drawback with these approaches is that none of them may match the exact particle, because it's all based on mathematical analysis. So, for example, if you have this particle, the shape that you actually come up with maybe, let us say, over here. So, it may be slightly different in elongation ratio, it may be slightly different in roughness, it may be slightly different in bulkiness, but the combination is such that gives you the minimum deviation from the actual shape. Now, that may not be acceptable again in certain applications. Of the three, you may say that bulkiness is my most important parameter, in which case what you will try to do in your algorithm is use that as your anchor. It is not enough if you just minimize the distance function or maximize the likelihood function. Also, you need an exact match for one parameter, and that is called the common property approach, that at least one property that you identify must be common between your candidate shape and your test shape. Okay, that is another approach, and which approach you choose depends obviously on your functionality. And the last one, clustering, again is sort of related to the common property approach. It says that if I have three properties that are important to me, and if I find that the best results are obtained when, let us say that you have a test particle, again let us say that it is here, and you have one candidate shape here and one candidate shape over there, where let us say the distance functions are approximately equal. So, it could be either one. Then what you look at as the next step is how the particles, the properties of the particles are clustered in the shape space compared to your actual particle. In other words, you look for not only the overall deviation, but you look at the deviation of individual properties from each other, and you try to minimize the sum of the individual deviations. So, it is sort of like the common property approach, except you are not saying that there is one property that is very important. What you are saying is that all three properties are equally important, and you want to minimize the deviation from each of these properties of shape. Okay. So, these are all, I would say, very subtle variations on the same theme, and they are all based on well established ground rules of pattern recognition. Shape analysis is a science, although the results that come out of it after extensive analysis, a scientist may say, I have done all this work, and this particle looks to me like it is spherical in shape or rod like in shape. So, the outcome from all this may be a simple verbal description, but there is a lot of very detailed analysis that can go into shape definition, and it is important in mechanical operations because the way particles behave depend very strongly on shape, and that is true also for the next parameter that we will talk about, which is size. But before we do that, do you have any questions on what we have discussed so far as shape analysis is concerned? We are pretty much done with that discussion. And again, like I mentioned in the last class, to get more details for all this, do go to my YouTube lecture. I think you can just type Nagarajan YouTube particle, and it will bring up the playlist. The lectures on shape characterization are from 3 to 5, I believe, and size characterization, the lectures are from 6 to about 12, if I remember right. So, what I am going to try and do again is summarize the information that is in lectures 6 to 12 within the next couple of lectures, but I do urge you to go back and take a look at these lectures, which will cover the same material in a lot more detail. I think you can also get there from going to the NPTEL website and searching by name or course title. Okay, yeah.
Deterministic and statistical. I'm not able to understand exactly what is it.
Well, as the name says, deterministic assumes you know everything about a system, right? Which is not always true, because especially when you get to particles in the nano range, they tend to move around a lot. So, it is like you can either know their velocity or their position, or but not both at the same time, right. So, when you try to estimate, for example, the shape of a particle, we are assuming when you put a point down there, it means you know everything, right, but that is not true. So, there is an error bar around each of these. So, what you are really trying to minimize is the distance between the error bars. So, you are assuming that there is a lot of uncertainty in the shape analysis of the real particle, and you are assuming that there is uncertainty in your library as well. So, you do not assume that everything is known and you just need to minimize absolute values. You are also trying to minimize the standard deviation, so to speak. So, it is a question of whether you deal with only the mean or you deal with the mean plus the standard deviation. Okay. Yeah.
How is clustering property approach different from distance function?
Well, in the distance function approach, what you are really trying to do is minimize the total distance, kind of an integrated version, right. You take the total deviation as an integration of the deviation in each of the 3 shape parameters. So, the expression that you get, or the final answer that you get, as I said, may be completely different from the real particle, because it is based on a mathematical technique. In both the common property approach and the clustering property approach, you try to go a step beyond that, and you try to say that I want at least certain parameters to be exactly same as in my test particle, okay. Not just based on a mathematical analysis, but based on a real inspection of values. So, in the case of the common property approach, you pick one property which you think is most important and you try to minimize the deviation from that. In the case of the clustering approach, you say that all these properties are important and it is not enough for me to minimize the integrated deviation from all the properties, I want to minimize the deviation for each of the properties. So, it is a more differential form of treating the same problem, okay. Anything else? All right, so let us move on to size characterization. Size is it is an absolute parameter in a sense, but not really, because how do you measure size? For big particles, you can just inspect by eye. If you want to know what is the length of this, I can just look at it and say it is 5 centimeters long or whatever. But if I keep breaking this down to smaller and smaller fragments, pretty soon you are not going to be able to do that, right. Your eye is going to run out of steam as far as being able to define the shape. So, as particles get finer, what do? You have 2 choices. One is you start using magnification. So, you try to put it under a magnifying lens, magnify it and look at it. It may be that sometimes if the particle is fluorescent, it shows up better under a fluorescent light. So, you try to use lighting, you try to use magnification, you try optical techniques. If optical techniques are not sufficient, you start using electron emission, electron scattering type of techniques. So, that is one way to go, which says I will keep examining this particle with more and more sophisticated methods until I can measure its size. The other approach would be to say that if the particle gets to be very fine, I am not going to waste a lot of time and resources trying to again pin down its size, because what I really need is to know how it is going to behave in my process, and therefore I am only interested in its size in the sense that in the context of how it affects my process. So, for example, if you have a process in which a particle is flowing in a pipe, then what you really want to know is how does the shape and the size of the particle affect its flow characteristics. So, then what would you do? Instead of trying to measure the particle size in a static mode individually, you set it in motion and you look at its flow behavior and you extract its particle, its size from its behavior in this dynamic mode. So, that is a more functional measurement of size, right. So, both these approaches are perfectly valid. In fact, size analysis can be broadly classified into 2 types: static analysis and dynamic analysis. In dynamic analysis, what you do is you set the particle in motion, observe its behavior, and from its functional behavior you extract size characteristics. Now, clearly this technique is more for particle populations rather than single particles, right, because you can take a whole powder and set it in motion of some kind and analyze size based on that. Dynamic methods have certain advantages. They are quick, they are cheap, and they are very functional. You know, you can actually relate the size you measure to something that's important in your process. So some examples of dynamic size measurement processes, you know, things that you will do in your mechanical operations laboratory next year, like sieving. We talked about sieving in the last class. Sieving is where you take a powder and you set it in a mesh and basically vibrate it, and then look to see how many particles are retained at various mesh sizes. Here what you are doing is you are not doing single particle analysis, right. You are taking this entire powder of particles, setting it in motion. In this case, what sets it in motion is the vibration of the sieve shaker, and then you look at how the particles are transported from one sieve to the next. And what will happen is, depending on the size of the particle, they will either pass down to the next sieve or they will be trapped in the previous sieve. So by simply looking at the dynamics of particles moving down from one sieve to the next in your sieve stack, you can classify the particle population into various size ranges. Now the limitation of the sieving method, for one thing, there is a size limit. Once you go below about 40 microns, sieves become somewhat ineffective. Although there are micro sieves now that can go down to 20 microns, but it is very difficult to control the dynamics of particles that are smaller than 20 microns in a mechanical sieve type of an apparatus. So typically sieve analysis is done for particles that are 20 to 40 micron sizes and larger. Another technique that you will use is sedimentation, where you look at how particles settle and you extract size information based on its settling rate. It is also called, well, the sedimentation technique can be used in multiple ways. You can take again a powder of particles and just drop it down a liquid column and use various techniques to measure how these particles move down the column to the bottom. You can also use what is known as Beaker decantation. You can take out liquid at various levels in your column and look at the particle sizes that are in that beaker. The idea here is particles will separate based on their size characteristics and they will sediment at different rates. By looking at the sedimentation characteristics, you can ascribe a size to it. Again, the advantage is it is a quick and dirty method. The disadvantage is settling is a phenomenon that can be affected by many things that are going on. For example, there is something called hindered settling, which happens when particles get too close to each other and they actually start interfering with each other's sedimentation characteristics. That can happen as your concentration increases, for example, and the distance of separation between adjacent particles is not very large. Also agglomeration, aggregation, all of these become possible when you have this type of a sedimentation happening. So they can all interfere with your size measurement. Now what is common to these techniques, whether it is sieving or whether it is sedimentation? What is common is they are not measuring an absolute size. What they are measuring is what we call an equivalent size. In the case of spherical particles, it will be called an equivalent diameter. So for example, if you are using a sieve to do size analysis, the size that you measure you would call a sieve equivalent diameter. If you are using sedimentation as a way of measuring size, you would call it a settling equivalent diameter. Or you can have a situation where you take particles and entrain them in a flow of air or a liquid, and then based on their mobility you classify them. In the laboratory we have something called an air classifier, which uses this a column of air to blow the particles up, and they follow different streamlines depending on their size. The lightest particles get blown out to the outside, the heaviest particles stay in the inner diameter. So in that case you are separating particles and you are doing size analysis based on their aerodynamic characteristics. So, then the diameter that you measure would be called the aerodynamic diameter, right. So, these are all equivalent diameters, they are not absolute diameters or absolute sizes, but sizes that are functionally derived. Okay. Another example is what we call a diffusion battery. If you have extremely fine particles, nano size for example, the predominant transport mechanism in the nano size is diffusion. So, you can similarly set up an experimental apparatus that looks at how particles move by diffusion, and you do your size analysis and you do your separation based on the diffusion characteristics of the particle. In that case, the size that you measure would be called a diffusion equivalent diameter or a diffusion diameter. So, the key thing to remember in dynamic size analysis is that what you are measuring is not the absolute size, but rather an equivalent size that depends on the mechanism that you are using to set the particles in motion. Okay. All right, any questions on that? So, in the next class we will start talking about static methods of analysis, and then we will continue the discussion of single particle analysis versus particle population analysis. See you in the next class.